Imagine a message sent from Earth almost 50 years ago, still traveling, still sending back whispers from the very edge of our solar system and beyond. This isn't science fiction. This is the incredible, ongoing journey of the Voyager spacecraft. These two robotic explorers, Voyager 1 and Voyager 2, launched in 1977, have gone further than any human-made object before them. They are now in a place we call interstellar space, the vast, cold, and mysterious region between stars. What are they finding out there, and how are they still working after all this time? Join us as we uncover the amazing story of Voyager's current journey. To understand where Voyager is now, we need to look back to where it all began. In the late 1970s, NASA had a unique opportunity. The giant planets of our outer solar system, Jupiter, Saturn, Uranus, and Neptune, were aligning in a way that happens only once every 175 years. This rare alignment allowed a spacecraft to use the gravity of one planet to slingshot to the next, saving huge amounts of fuel and time. This was called the Grand Tour. Voyager 1 and Voyager 2 were designed to take advantage of this. They were built to be tough, with instruments that could study these distant worlds. Each Voyager spacecraft is about the size of a small car, with a large dish antenna for sending and receiving signals from Earth. They also have a long boom for their magnetometers, which measure magnetic fields, and other instruments to study particles and waves in space. Voyager 1 visited Jupiter in 1979 and Saturn in 1980. It then used Saturn's gravity to speed up and head out of the plane of the planets on a path that would take it out of our solar system entirely. Voyager 2 followed a different path, visiting Jupiter in 1979, Saturn in 1981, Uranus in 1986, and Neptune in 1989. This made Voyager 2 the only spacecraft to ever visit Uranus and Neptune up close. After their planetary encounters, the Voyagers continued their journey, heading towards the edge of our Sun's influence. Our Sun creates a giant bubble of charged particles and magnetic fields called the heliosphere. Think of it like a giant invisible shield around our solar system. Inside this bubble, the solar wind, a constant stream of particles from the Sun, flows outwards. As the Voyagers traveled further, they started to encounter the boundaries of this heliosphere. The first boundary they crossed was the termination shock, where the solar wind slows down dramatically. Beyond that is the heliosheath, a turbulent region where the solar wind mixes with the interstellar medium. It's like the foamy wake behind a boat. Finally, they reach the heliopause, the true edge of the heliosphere, where the solar wind is stopped by the pressure of the interstellar medium. This is the boundary between our Sun's domain and the vast uncharted territory of interstellar space. Crossing this boundary was a historic moment for humanity. Voyager 1 officially entered interstellar space in August 2012, becoming the first human-made object to do so. Voyager 2 followed in November 2018. This was a huge achievement, allowing us to directly study the space between stars for the first time. Before this, all our knowledge of interstellar space came from observations made from within the heliosphere. What did they find? One of the most exciting discoveries was the detection of a faint plasma hum in interstellar space by Voyager 1. This hum is caused by the vibrations of dense interstellar plasma, which is ionized gas. It's like hearing the gentle rain, but in space. This discovery helped scientists understand the density of the interstellar medium. Voyager 1 also found that the magnetic field lines in interstellar space are different from what they expected, showing that our understanding of this region is still evolving. It's truly remarkable that these spacecraft, launched in the 1970s, are still operating. They are powered by radioisotope thermoelectric generators, RTGs, which convert heat from the decay of radioactive plutonium into electricity. This power source has allowed them to continue their mission far beyond the reach of solar panels. However, the power from the RTGs is slowly decreasing. To extend the mission as long as possible, NASA engineers have been carefully managing the power, turning off instruments one by one. Originally, each Voyager had 11 scientific instruments. As of March 2025, both spacecraft have 3 operational instruments, with plans to reduce to 2 in 2026. Some of the key instruments still active include Cosmic Ray Subsystems (CRS), This instrument measures cosmic rays, which are high-energy particles from outside our solar system. By studying these particles, scientists can learn about the origin of cosmic rays and the conditions in interstellar space. Low-energy, charged particle, LECP. This instrument measures the flow of charged particles. It helped determine when the Voyagers crossed into interstellar space by detecting changes in the types and energies of particles. Magnetometer MAG. This instrument measures magnetic fields. It has been crucial in understanding the magnetic environment of the heliosphere in interstellar space. These instruments continue to send back valuable data, even though the signals take a very long time to reach Earth. For Voyager 1, it takes over 22 hours for a signal to travel one way. This means that communication with the spacecraft is a slow and patient process. The Voyager mission has faced many challenges over its long life. From instrument failures to power limitations, engineers on Earth have had to come up with clever solutions to keep the spacecraft going. In November 2023, Voyager 1 stopped communicating properly, sending back garbled data. Engineers worked tirelessly for weeks and successfully restored contact in December 2024. A testament to their dedication and ingenuity. The future of the Voyagers is uncertain, but their mission continues to push the boundaries of exploration. They are expected to continue sending back data for a few more years, until their power levels become too low to operate any instruments. Even after they go silent, they will continue their silent journey through the galaxy, carrying the golden record, a message from Earth, to any intelligent life they might encounter. Both Voyager spacecraft carry a special artifact, the golden record. This 12-inch gold-plated copper disc contains sounds and images. Selected to portray the diversity of life and culture on Earth, it includes greetings in 55 languages, sounds of nature, music from different cultures, and images of people, places, and scientific diagrams. It's like a time capsule, a message in a bottle, cast into the cosmic ocean for billions of years. The Voyager mission is an incredible testament to human curiosity and ingenuity. For nearly 5 decades, these two small spacecraft have been exploring the farthest reaches of our solar system and beyond. Sending back groundbreaking data that has reshaped our understanding of the cosmos, they have shown us the beauty of the outer planets, the boundaries of our sun's influence, and the mysterious nature of interstellar space. As the Voyagers continue their silent journey, they remind us that exploration is an ongoing process, a continuous quest to understand our place in the universe. They are truly humanity's farthest ambassadors, whispering tales of our home planet to the vast, silent expanse of interstellar space. Jupiter, the largest planet in our solar system, was the first giant visited by both Voyagers. Voyager 1 captured stunning images of Jupiter's Great Red Spot, a massive storm larger than Earth that has raged for centuries. It also discovered active volcanoes on Io, one of Jupiter's moons, a completely unexpected finding that revolutionized our understanding of planetary geology. Voyager 2 provided even more detailed observations of Jupiter's atmosphere and its complex system of rings and moons. Both spacecraft journeyed to Saturn, famous for its magnificent ring system. Voyager 1 made close observations of Saturn's rings, revealing their intricate structure and the presence of spokes, temporary features that appear and disappear. It also studied Titan, Saturn's largest moon, and found it to have a thick atmosphere, making it a prime target for future missions. Voyager 2 continued these studies, providing more data on Saturn's atmosphere, rings, and moons. Voyager 2 then embarked on a solo journey to the ice giants Uranus and Neptune. At Uranus, it discovered 10 new moons and 2 new rings, and found that the planet's magnetic field was tilted at a strange angle. This was a puzzling discovery that scientists are still trying to fully understand. The spacecraft also observed Uranus's unusual rotation as it spins on its side. Finally, Voyager 2 reached Neptune, revealing its dynamic atmosphere with strong winds and a great dark spot, similar to Jupiter's Great Red Spot, but much darker. It also discovered 6 new moons and 4 new rings around Neptune. The most surprising discovery at Neptune was Triton, its largest moon, which was found to be geologically active with geysers erupting nitrogen gas, making it one of the coldest, yet most active, bodies in the outer solar system. These close-up encounters with the outer planets provided a wealth of new information. transforming our understanding of these distant worlds from blurry telescopic images to detailed portraits. The data collected by the Voyagers continues to be analyzed by scientists today, yielding new insights into the formation and evolution of our solar system. The heliosphere is not just a simple bubble. It's a complex, dynamic region shaped by the sun's activity. Imagine our sun as a giant cosmic lighthouse, constantly emitting a stream of charged particles called the solar wind. This solar wind travels outward in all directions, creating the heliosphere, acts as a protective shield for our solar system against harmful interstellar radiation. As the solar wind expands, it eventually encounters the thin gas and magnetic fields of interstellar space. This encounter creates several distinct boundaries that the Voyager spacecraft have crossed. The first is the termination shock, where the solar wind, which has been traveling at supersonic speeds, suddenly slows down to subsonic speeds. This is similar to a sonic boom, but in reverse, as the wind hits a wall of resistance from the interstellar medium. The Voyagers detected this boundary by observing changes in the speed and direction of charged particles. Beyond the termination shock lies the heliosheath. This is a vast, turbulent region where the slowed-down solar wind is compressed and heated as it interacts with the interstellar medium. Think of it as a cosmic traffic jam, where particles from the sun and particles from interstellar space are jostling for position. The Voyagers spent several years traversing this region, providing invaluable data about its structure and composition. They observed fluctuations in the magnetic field and changes in the energetic particle populations, indicating the complex interactions occurring here. Finally, the Voyagers reached the heliopause, the outermost boundary of the heliosphere. This is the true frontier where the outward pressure of the solar wind is balanced by the inward pressure of the interstellar medium. Crossing the heliopause was a monumental achievement, as it marked the first time human-made objects had entered interstellar space. At this boundary, the magnetic field lines from the sun are thought to reconnect with the magnetic field lines of interstellar space, allowing some interstellar particles to enter the heliosphere and some solar particles to escape. Studying these boundaries has been crucial for understanding how our solar system interacts with the wider galaxy. The data from Voyager has helped scientists refine their models of the heliosphere and its role in protecting life on Earth from the harsh environment of interstellar space. It's like having a direct probe into the very edge of our cosmic neighborhood. The heliosphere is not just a simple bubble. It's a complex dynamic region shaped by the sun's activity. Imagine our sun as a giant cosmic lighthouse, constantly emitting a stream of charged particles called the solar wind. This solar wind travels outward in all directions, creating the heliosphere, which acts as a protective shield for our solar system against harmful interstellar radiation. This encounter creates several distinct boundaries that the Voyager spacecraft have crossed. The first is the termination shock, where the solar wind, which has been traveling at supersonic speeds, suddenly slows down to subsonic speeds. This is similar to a sonic boom, but in reverse, as the wind hits a wall of resistance from the interstellar medium. The Voyagers detected this boundary by observing changes in the speed and direction of charged particles. Beyond the termination shock lies the heliosheath. This is a vast, turbulent region where the slowed-down solar wind is compressed and heated as it interacts with the interstellar medium. Think of it as a cosmic traffic jam, where particles from the sun and particles from interstellar space are jostling for position. The Voyagers spent several years traversing this region, providing invaluable data about its structure and composition. They observed fluctuations in the magnetic field and changes in the energetic particle populations, indicating the complex interactions occurring here. Finally, the Voyagers reached the heliopause, the outermost boundary of the heliosphere. This is the true frontier, where the outward pressure of the solar wind is balanced by the inward pressure of the interstellar medium. Crossing the heliopause was a monumental achievement, as it marked the first time human-made objects had entered interstellar space. At this boundary, the magnetic field lines from the sun are thought to reconnect with the magnetic field lines of interstellar space, allowing some interstellar particles to enter the heliosphere and some solar particles to escape. Studying these boundaries has been crucial for understanding how our solar system interacts with the wider galaxy. The data from Voyager has helped scientists refine their models of the heliosphere and its role in protecting life on Earth from the harsh environment of interstellar space. It's like having a direct probe into the very edge of our cosmic neighborhood. When Voyager 1 crossed the heliopause in 2012, and Voyager 2 followed in 2018, they didn't just enter a new region of space, they opened a new chapter in our understanding of the universe. It's filled with a very thin, cold plasma, cosmic rays, and magnetic fields. The Voyagers are providing us with the first direct measurements of this environment. One of the most fascinating discoveries was the detection of the plasma hum by Voyager 1. This hum is essentially the sound of the interstellar medium vibrating. It's caused by electron plasma oscillations, which are tiny disturbances in the ionized gas. By studying this hum, scientists can determine the density of the interstellar plasma. This is crucial because the density of the interstellar medium varies, and understanding these variations helps us map out the local interstellar environment. The hum also provides clues about how the heliosphere interacts with the interstellar medium. As these oscillations can be triggered by shocks propagating through the plasma, another key finding relates to the magnetic fields. Before Voyager, scientists had models of what the interstellar magnetic field might look like. However, Voyager 1's measurements showed that the magnetic field lines in interstellar space are oriented differently than predicted. This suggests that the interstellar magnetic field is more complex and perhaps more turbulent than previously thought. These magnetic fields play a vital role in shaping the flow of interstellar gas and cosmic rays. So understanding their structure is fundamental to comprehending the broader galactic environment. The Voyagers are also providing unique insights into cosmic rays. These high-energy particles originate from supernova and other violent events in our galaxy. Inside the heliosphere, the Sun's magnetic field acts as a partial shield against these particles. But in interstellar space, the Voyagers are exposed to the full flux of galactic cosmic rays. By comparing the cosmic ray measurements inside and outside the heliosphere, scientists can better understand how the heliosphere protects us and how cosmic rays propagate through the galaxy. This has implications for understanding radiation hazards for future human missions beyond Earth's protective bubble. These discoveries are not just about filling in blanks on a map. They are about fundamentally changing our understanding of our place in the galaxy. The Voyagers are our eyes and ears in a region that was once purely theoretical, revealing a dynamic and complex environment that continues to surprise us. As the Voyagers continue their silent, endless journey, they serve as a powerful reminder of humanity's insatiable drive to explore, to understand, and to reach beyond the known. They are not just machines. They are extensions of our collective curiosity, carrying our hopes and dreams into the vast, silent expanse of interstellar space, forever whispering tales of a small blue planet and its ambitious inhabitants.